Alright, so comparing two sample means. And to motivate this, let's try to think about this hypothetical scenario. So the new fertilizer is developed specifically for tomatoes, and the company is claiming that their product is about the same price as the generic one, but they're more effective because they're specifically targeting for tomatoes. So a farmer wanting to verify that indeed if using this new fertilizer is going to give him more tomatoes, he applied them to 50 cherry tomato plants and compared it to another 50 tomato plants that were treated with generic fertilizers. Okay? And then, so he waited same number of days. I don't know, like, does it take 2 months? I don't know. And then he would go to the trees and then get the tomato fruit from each one of these. And the ones with the fertilizer treated, he gets 51, 59. Oh, just a minute, I got the numbers backwards. Sorry, this should be generic. This should be generic. This would be new, right? Okay. So for the generic treated ones, he gets like 51, 59, and then 57. Well, here it looks like this one's bigger than the other ones. But anyways, he counts all the number of tomatoes he gets. And then he has this question. Can we conclude that the new fertilizers is more effective than the generic one at 0.05 significance level? And that's the question that we want to answer. Before we actually move on to doing this, we will have to develop some theory of being able to compare the two means. And here, x is the variable for the generic ones, and y is the variable for the fertilizer ones. And the question here is the mean value of mu really less than the mean value of y? That's the question that we want to know, right? Where we don't know the true mean because it's impossible to grow all the possible tomatoes that mankind can ever eat. That's not possible. So we don't really know the true mean value. What we have is just the sample mean. Okay? So we have access to the following. We have access to the sample mean and the sample mean of this other one. Okay? And what we are going to assume are the following things. First, we're going to assume that the number of tomatoes from the first group and the second group are not related to each other. Okay? They're just independent. Okay? Like having 51 from the first plant, is that going to say certain plants in the second group is going to produce more? No, it doesn't make sense, right? So they should be independent. So here we're really comparing two sample means when the two samples are independent. Another thing we're going to assume is that the sample size is large enough so that we don't have to use any t-distribution. So I talked about this t-distribution. When your sample size is too small, then because you don't know the population standard deviation, that causes additional uncertainty, which forbids you from using the usual normal distribution. Instead, you have to use a distribution that's slightly more spread out. Spread out means there's more uncertainty, okay? So there's something that has more uncertainty so that you have to use that in order to get a better conclusion. and I explained what t-distribution is, but if you want to use t-distribution, you need to use the degrees of freedom. Degrees of freedom in the t-distribution is defined as the number of data points minus 1. But that causes additional problem because there's one data point, there's another data point. So what should you use for degrees of freedom? Well, there is eventually a formula for finding the degrees of freedom in that case, but it's just more complicated. So I'm not going to do it that way. Instead, what I'm going to explain here is assuming that our data size is big enough that we don't have to use a t-distribution. See, the rule of the thumb is that if you have 30 or more samples, then the normal distribution is pretty good approximation to the t-distribution. Some people say 100, but I mean, the bigger the number becomes, the better your approximation of the population standard deviation becomes, and therefore there's less uncertainty. And you can actually see that when you send degrees of freedom to something really large, the t-distribution becomes closer and closer to the normal distribution. So we don't have to use the t-distribution if you have bigger sample size here. The sample sizes are 50 and 50, so definitely we don't need to use the t-distribution in this case. Okay, so we're just going to use the normal distribution. And to use the normal distribution, that means we have to find the z-score. To find the z-score, we have to know the mean value and the standard deviation. But the problem is, in order to find the mean value and the standard deviation, we're not talking about the mean value of each of one of them, and we're not talking about the standard deviation of each one of them. We're talking about this quantity. We want to show that this is negative, right? We want to show that this is negative, right? So we want to show that, actually we want to show that mu x minus mu y is negative, right? And to show this, we have to show that this is negative and it's strongly negative enough that with a certain level of significance, you can say that it must be negative, even for this one. If this is strongly negative at the 0.05 significance level, then you can conclude that this is negative with 95% probability. So that's what we want to do. So now, what I'm trying to explain so far is that with this setup, we're really interested in this quantity. What is the probability distribution of x bar minus y bar? That's the question, okay? Now, first of all, with the central limit theorem, if the original thing is approximately normal, we just did the homework on that, right? Even if the initial probability distribution is highly skewed, if you do many samples and take the mean values, and then mean values of the sample become closer and closer to normal distribution, right? So, and you can kind of like assume that, well, this is about number of tomatoes. I think that should be about a bell curve. It might be skewed towards one or the other, but it should be probably something like a bell curve. So you assume that this is something like a bell curve. This is somewhat close to the bell curve, and then if you take samples, these will be separately more and more like even closer to a normal distribution, right? And then the property of the normal distribution is that if you have two normal distributions, then you can add or subtract them, or you can take many of them and take the averages of them. All of these still become normal distributions. Their average and standard deviation will be different, but they'll still be bell curve, okay? So that's what we know about this. Therefore, in order to determine the distribution of this, once you know that this is a normal distribution, you only need to know two things. Normal distribution just has two parameters. The mean value, and what's the other one? A normal distribution is determined by the center point and standard deviation, which is like how spread it is, okay? So we just have to know those two things, okay? All right, so let's first find the standard deviation. Well, let's first find the mean value. Well, this is easy. The property of a mean value is you have E of x bar minus E of y bar, right? And I know that this value is same as the true mean. This value is same as the true mean. So if you take these sample values and you do the sampling many, many times and take their average, it's going to converge to the true mean values, right? So that's what we have. Another thing is you have, so now you need the standard deviation. So you have to calculate the variance because the standard deviation is the square root of the variance. So let's try to do V of x bar minus y bar. And for this one, we can use the formula that variance of any random variable is that random variable squared, and you take the average minus, you take the difference average and then take the average and then square. So it's the average of the square minus square of the average. If you do average of the square minus square of the average, that gives you the variance. That's the formula. And we can just expand this just using what a minus b squared is a squared minus 2ab plus b squared. Everyone knows this, right? So we can use that, and you get E of x bar squared minus 2x bar y bar plus y bar squared minus, this one is same as, I wrote it here, it's EX minus EY. So it will be EX bar squared minus 2EX bar EY bar plus EY bar squared. So just write them out. And again, because E is linear, you can just put them here. And you can immediately see that the first, let me just continue my calculation here. You have E of x bar squared minus E of x bar squared. Okay, so you have this one thing, and then E of y bar squared minus E of y bar squared, and then plus negative E of x bar E of y bar, and then there's a minus of minus, so it's plus 2E of x bar y bar. What is this same as? It's the variance of x, right? So this would be the variance of x. And the second one is the variance is standard deviation squared, so I'm going to write it like that. And the second thing is variance of y squared. There's something that I got wrong, sorry. This is not the variance of x itself, it's the variance of x bar, but if you take the averages, what happens to the variance when you take the averages? Once you take more and more averages, the variance becomes smaller, right? Their fluctuations become smaller once you take more samples and take averages. And how smaller does it get? Divides by n, right? Okay? So the variance, without this, this is the original, let me write down sigma. Okay, so sigma 1 would be the variance of the population from the ones that were treated by the general fertilizer. and sigma 2 will be the variance of the population, the ones that are treated by the new fertilizer. Okay? So I'm going to write this as sigma 1 and sigma 2. And because the first one, we're taking the average, the variance of the average. So x bar is, this bar means average, okay? So this really is like x1, the values, the 50 tomatoes, the 50 different number of tomatoes you obtained from the 50 tomato plants. So that's what x bar is, okay? So this 50 will be our n, okay? But I want to show you a formula for a generic case, so I'll just write this as n1, which is whatever that's down here. Okay? It's the number of samples that you get from group A, the first group. Okay? So it's the first group's variance divided by the variance of the number of data points of the first group. And you divide, for this one, you divide it by n2. Okay, so that's what it is. Now, what about this? What can you do with this? Huh?
You cancel it out.
Why? Why do they cancel out?
Because the e of x bar times e of y bar is the same as e of x bar times y bar.
Why?
Because they're independent.
Yes! That's perfect. Yeah. Wow, okay, so I didn't expect anyone to catch that. Yeah, so we know that if two random variables are independent, then this is true, right? Now, in general, if there is some kind of correlation between the two, then it's not true that they're independent. So you can think of something like this quantity, e of xy minus e of x times e of y, to see how much do they differ. If this is perfectly zero, then you say that those two samples are independent. And you know, by chance you might have a slight correlation, but the values will still be, if they're truly independent, the values will still be very close to zero, okay? For our specific sample set. But this is like in general, so you're taking the averages after repeating the samples many times, so that's why this is zero if it's truly independent. But then, if this is not zero, that means they have some kind of correlation between them. Okay, so this has a name. This value is called covariance of x and y. It just measures how much these two things differ. Right? Okay. So, anyways, we know that our assumption is that the two samples are independently sampled. So there shouldn't be any correlation between them, therefore this value should be zero, which means this is what we get. Okay? And therefore, we see that the standard deviation that we use for the difference of two mean values is the standard deviation squared divided by n1 plus standard deviation 2. It's hard to draw sigma. It looks like a 6, so be careful, okay? You don't want to write 6. This is not 6, this is sigma, okay? Only a tiny little bit should be sticking out. Okay? Alright, so you have that and then n2. Okay, so with these two mathematical conclusions, we are ready to tackle this problem. All right, so let's try to tackle this problem. Okay, so first of all, we have these values, and how do you get the average of x? So what is our x bar?
Sum of x divided by 50.
Right, so it should be 2780 divided by 50, right? So, what's that? I have my calculator. It's 55.6. And then y bar would be 3020 divided by 50. So we 3020 divided by 50. 60.4. And that tells us, from this, it tells us that x bar minus y bar is 55.6 minus 60.4, which is 0.8, 4.8. Oh, negative 4.8. So we have negative 4.8, which seems like a big enough difference. You see that on average, the new fertilizer treated ones gave you about 5 cherry tomatoes per plant more. And if you own a big farm, that could be meaning something. So that's nice. But with just 50 samples, can you just say that this one really is better than the other? How do we know? So that's something to think about. So let's continue on. Now, because we have this, we need to calculate sigma 1 and sigma 2 separately. Okay, so what is sigma 1 squared? Sigma 1 squared is the variance of this thing, the x itself. It's not x bar. Variance of x, and therefore this is e of x squared minus e of x squared. And what is e of x squared? That means it's the average of x squared values. We have the sum of x squared values here, right? So how do we get the average? 178,000 divided by 50, right? Minus 55.6 squared. Okay? So let's try that. So you have 178,000 divided by 50. So you have 3560 minus we get 3091.36, and that gives us 468.64. Okay. However, there's a slight catch. This is a sample variation, but it's the variation of the sample itself. But what we want is, this is really, I don't know what, it's a variation of the sample itself. So what we really want is, in here, we really want the approximate value of the population variance, right? So to get the population variance from your sample variance, what do? There's a slight, these tend to always underestimate, right? So there's some kind of correction you have to do in order to make it correct.
The Bessel correction?
It's called the Bessel correction, right? So what this is 468.64 is really it's the x minus mu squared divided by n. That's what's being calculated. But what we want is, we want it to be divided by n minus 1. Right? Variance is how far away each item is from the mean value. You square them so it's all positive. You add them up and you want to calculate the mean value. That's what variance is. It tells you how spread apart your data is from the mean value, right? But then this tends to underestimate just because you're really not using mu. In practice, you don't have the access to mu. You end up using x bar as an approximate. And that tends to be like going along with the actual values itself. So this fluctuation, that measurement that you do, is underestimating the true fluctuation of the population data. So you have to instead divide by n minus 1, but here's how you think. So this must be, you can think of this as n over n minus 1 times 1 over n sigma x minus mu squared. See, n and n will cancel if you just stick an n here and there, right? But what is this? This is this value, right? And what's our n? What's
50.
our n? 50. So what you have to do is you have to do 50 divided by 49 times 468.64. So let's see. Times 50, and then you have to divide by 49. So that ends up giving you 478.2. So it's slightly bigger. Is that really? Oh, okay. So it should be right. Okay. So that's what you need. Now let's go for the second one. Same procedure. Oh, I raised it. What was the average of the second one?
60.4.
60.4. Okay, so you had to get an estimation of sigma 2 squared, or let me write down V of x y bar is E of, is the average of the squared, I shouldn't put the bar here, sorry. V of y, then it's the average of the squared minus square of the average, and that one is 1 over 50 times 189,000 minus 60.4 squared. Okay, so 189,000 divided by 50 minus 60.4 squared gives you 131.84. Okay, so this has a smaller variance. And again, to actually get a best approximation, you have to multiply by 50 over 49. So you have to multiply by n over n minus 1, 131.84. So you multiply by 50, divided by 49, and you get 134.5. Oh, this is squared. This is really, this is sigma x squared. All right, so now we are ready to calculate the standard deviation of the total, the actual difference. So this is the standard deviation of x bar minus y bar, which is the square root of the first sigma, 478.2, divided by the number of samples that you used, which is 50 here, plus 134.5 divided by 50. All right, so let's try that. So this is a square root of 12.25. And if you take the square root, I get 3.5. Okay, so that's our standard deviation. So we had, so what we now see is the following conclusion. So what we find is that x bar minus y bar follows the normal distribution of, no, that's not what I do, sorry. Now I have to do a z-score. Okay, so now let's calculate the z-score. Z-score is, the usual definition is you have x minus mu divided by sigma. Right? All right, so okay, I'm doing things out of order, so let me go back and start start doing the hypothesis testing, because now I have all the values. All right, so we're eventually going to use this test statistic, and we will also what's the value? We also have the e of x bar minus y bar as negative 4.8. Okay, we did all the calculations just to show you what kind of calculations are involved, but now let's actually do the hypothesis testing. And we're going to do the classical 4-step hypothesis testing. Okay, what is the first step of hypothesis testing? Step 1. So we did this before the spring break, so I don't blame you if you can't remember. Step 1 is, yes?
You have to form an alternative and null hypothesis.
Right, you have to put the H0 null hypothesis and alternative hypothesis. Okay? So the null hypothesis is the one that the assumption that you use in order to do the statistical analysis. Okay? And for hypothesis testing of mean, it's the mu value equals to something. So in our case, we're saying that the mu1 minus mu2, generic minus the nu, has to be equal. It's always equal to something for hypothesis testing of mean. And also for the proportion, it's this. Okay? Later on, we'll have different types of hypothesis testing. So we are going to be seeing some other variations, but at least for the hypothesis testing of mean or the proportion, the null hypothesis always takes the form of something equal to something. Because only when you say something is equal to some value, you can start to calculate things. If you don't know the exact value, or you can't assume some exact value, you can't do any calculation because you don't know the values, right? So it's always this way. And what are you trying to prove? You want to show that mu1 minus mu2 is less than 0, right? So that mu2 is bigger. We want to show that the new fertilizer gives you more tomatoes. That's what you want to show. Okay. Step 2. You have to find the rejection region. So, because you're given 0.5 significance level, you have to keep that in mind. The rejection region has to have 0.05 as its area, because area of the probability distribution corresponds to probability. Okay. But then there are 3 types. There's left tail, two-tailed, or there's the right tail. There are 3 types. And which one of the 3 is it? It depends on what the alternative hypothesis is. Okay? So seeing this, which one of these 3 is it?
Left tail.
This one is because it's less, right? If you want to prove something's bigger, then it's the right tail. If you simply want to show that this is not equal, then it's two-tailed, right? So this is the left tail. So let's try to figure out the rejection region with the left tail. You can use the chart to figure out what this value is. But a quicker way to do it would be inverse norm. So if you have a TI-84, please do this with me so you can let me know what value it is. So inverse norm, you just need to put 0.05 and 0.1, which tells you what is this question mark, what is this point, so that from negative infinity until this point gives you 0.05 probability. 0 and 1 means it's the standard normal distribution. So what do you get?
Negative 1.64.
1.64? Okay, negative 1.64. Okay. So what that means is that the rejection region is z less than negative 1.64. So your z-score, your test statistic that you compute afterwards, better fall in here in order to reject the null hypothesis and prove that, in fact, the new fertilizer is more effective. Okay? But now it's step 3. So in step 3, what do you do? Step 3 is when you compute the test statistic. So step 3, compute test statistic. So far, all of the hypothesis testing that we've done were either z-score or t-score. The formulas for the t-score or the z-score are exactly the same. It's just to remind you that one follows the standard normal distribution, the other follows the t-distribution. T-distribution requires degrees of freedom, which is more work. Just because our sample size is big enough, it's more than 50, so we can just use the normal distribution. Okay, so let's compute the z-score. So z-score of this difference, right, that we've computed is going to be, what do we know? It's negative 4.8, right? Minus, what's a purported value of the difference? Is 0, right? So maybe I should write down the formula before I proceed. So what I'm doing here is I'm comparing the sample difference between the means minus the purported difference between the means. Okay? And I want to see how they differ. If they differ by a lot, then it's unreasonable to think that this value should be 0. Okay? Then that's what we're trying to do. Divided by square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So this is going to be our formula. This is going to be the formula that you use for hypothesis testing of two samples that are independent, and you're comparing. When you're comparing two means from two independent samples, this is the formula that you use, assuming that your n1 and n2 are both bigger than 30, right? Okay. So now let's actually do it. I know that this value is negative 4.8 minus this value, we assumed it to be 0, divided by, we already computed this was 3.5. Okay, so let's see what that value is. 4.8 divided by 3.5, you get negative 1.3714. Okay. And then step 4, you have to draw a conclusion. All right, so what's our conclusion? Question is, does the test statistic belong to the rejection region?
No.
No. Z has to be left of negative 1.64 in order to fall into the rejection region. This one is somewhere here on the right side. So that means it's not highly unlikely that this would happen by chance. Okay? I mean, what you're seeing seems to be somewhat indicating that this is better than the other, but if you insist that you want to know for sure at 95% confidence level, then you can't really say that. You're not confident enough to say it that way. Okay? So we failed to reject the null hypothesis because negative 1.37 does not fall into in the rejection region. Okay? It doesn't fall in the rejection region, so we cannot say with 95% confidence you're sure that this is not zero. It could still have been zero, it's just that somehow the way that it was sampled or the way the experiment was done just happened to be that way, because in real life there are many things that just happen for random reasons, right? Okay, so we may not conclude, or we cannot conclude the new fertilizer is better from this data. Now a few more comments here. Failing to reject the null is different than being able to prove the null. There's a very big difference here. Okay, we just failed to say otherwise. This could still be false. We don't know, right? And in fact, the culprit may be just the sample size. Okay. The fertilizer factory, upon hearing this farmer's experiment and seeing the disappointing result, might say, hey, we'll give you more fertilizer for free. Try it on an additional 50 trees. And what happens is that if you have bigger sample size, if this becomes 100 instead of 50, okay, then overall this value will shrink, which means this value will shrink. If this value will shrink, then you get bigger negative value. And now that's going to fall in the rejection region. Okay, so that can also be done. So that actually happens in the lab. See, all these, any kind of experiment that you do, number n has to do with money, like, and time. Right? So sometimes you might do an initial sample of 50 of them, and you do see some kind of a trend, which, I mean, if I was doing an experiment like this and seeing something like this, I'll be like, oh, there's something here. We should make sure that this is true. But you can't prove it unless you have more experiments. If you have more and more experiments, then you'll be able to distinguish whether this is a statistical fluke or a real effect. And actually, it could turn out that if you do 50 more plants for each, the outcome of the next batch doesn't show a stark difference of negative 4.8 between the two, and you still have an inconclusive answer. Okay? So when your effect size is very small, then what that means is that you may have to run your experiment with like lots and lots more samples. So there's some cases where some kind of effect sizes don't show up at, say, 1,000 samples. You really need to look at like 10,000s of samples to actually show that, oh, this group A is like maybe 3% better than this group B, or something like that. So things like that happen. Okay? And so in other words, if you want to have more confidence, or if you want more, okay, so when you have a better significance level, that means the significance level is lower. Okay, so if you want better significance level, then you need to increase the sample size. So that's something that we learned here. Okay. Any questions?